Hello and welcome to just another FLUXANA XRF webinar. My name is Susan Aschenbrenner and we will have a look into the analysis of recycling material using X-ray fluorescence analysis today. If you have any questions during the presentation, please feel free to use the Q&A section to ask the questions. And yeah, I would say let's dive right into the topic and see how we can analyze recycling material. But first of all, why would we even use recycling material in the first place in our process? So first of all, when we are talking about recycling material, we are talking about saving money. We have less purchases of new and maybe expensive materials when we can recycle materials that is already there. Also, we are talking about conservation of resources. So keeping the material that is already used and not getting new material makes sense when we are looking at things that are coming from ending resources. And then a term that is with us for many years now in private and in the industry is the term sustainability. So by recycling different materials, we also want to have some sustainability added to our process. Using recycling material can have several challenges during the process. Let's have a look which challenges it can have for measurement of these recycling materials. First of all, there might be unexpected sample material. Since we are taking recycling material from a process and then try to recycle it and to use it again, the material itself before the recycling is happening might have some unexpected components, maybe a slightly different matrix than you would expect in the first place. And this makes measurement and decision making for calibrations quite tough. Then also there's the challenge that we have little or no reference materials available, especially when we are talking about very specific recycling materials. Most of the time there's not even one reference material that we can use. So we don't have any reference with which we can see if we are getting true results. And this can cause major stress. And also we have to have a look into time management. If we are buying a new material that is already pure and there's no contamination inside and so on and so on, we don't even have to take the time to measure it beforehand, or we can take less time because we don't have to think about unexpected components in sample materials and all these things that I talked about before. So the time management here can be a problem with recycling material compared to when we're using material that is not recycled. The question for today's webinar is how can XRF help us to analyze our recycling materials in an efficient way. And to kind of lead to this topic, I would like to start with the advantages that XRF measurements have. So first of all, with an XRF spectrometer, we can measure in a very large range. We can basically measure starting from the element of fluorine and then up until uranium. So this is a very large range throughout almost the whole periodic table. And we can measure a lot of elements by using one measurement technique. And this is one of the big advantages. Also, our method is non-destructive, so our sample is not harmed during measurement. And XRF is also a very long-term stable method. So if I am calibrating my machine today and I have a nice calibration that meets all my expectations and all my needs for my measurements that I'm doing, I can use it today, I can use it tomorrow, I can use it in 10 years, and it will be long-term stable. Another good point is that we are able to measure traces as well as main and side components. So we are not limited in this field that we can only measure traces or that we can only measure main components with our method. We can measure from ppms to 100%, obviously depending on our sample preparation. We are obviously still limited by our detection limit, but yeah, this has to be looked at depending on the sample and on its preparation. In general, the range here is also very broad. The spectrometers, when they are calibrated, they are easy to use. So as soon as the calibration is up and running, the sample just has to be loaded, button has to be pressed, and then the measurement can start. So this is also a big advantage. And in my opinion, one of the biggest advantages of XRF for these kind of application, for recycling applications and in general applications where we don't know from the beginning which kind of material and component we are dealing with, is the standardless software packages. Most of the XRF devices are coming with a standardless software, so-called standardless software. This means that this is a software that is already calibrated and without you calibrating on your side, you can do first screenings. It's just a mathematic way of viewing the collected data, and you can really greatly use it for semi-quantitative qualitative screenings. So if you really don't know what's inside of your sample, you can measure it, evaluate with a standardless software, and then you will have at least an idea of what is inside your sample without having the effort to calibrate in the first place. So knowing all of these things and having it in the back of our heads, we can now look through different kinds of recycling materials. I try to take some examples that we maybe know from our private or our workplace life to make it a little bit more interesting. So today we will have a look into recycling of glass, of plastics, of metal, and of catalysts. And we will also have a look into all the challenges that are coming with these different materials. What I cannot do today is give the perfect way how to analyze and prepare these different kinds of materials, because also within these groups there's a large variety of different materials, of different samples. that all have their own challenges, that all have their own specialities. And if you have some trouble with one certain material and you really need to know how to prepare or measure the certain material, please contact me later, and then we can talk about the very special application there. Here, I just want to give an overview and show what is generally possible when using XRF. So let's start with glass. At least in Germany, the glass recycling is a very common process. What is happening here is that that everyone is sorting their glass waste at home. We are sorting in colored and white glass, or sometimes, depending on the region where we are living, even in brown, green, and white glass. The glass is then collected in these kinds of containers that are also differentiating between brown, green, and white glass. And then it is basically already pre-sorted at home when it comes into the recycling process. Within this recycling process, there are still several sorting and testing points. Why is that happening? Well, basically, sometimes it still happens that a brown glass is coming to the green glass container or to the white glass container and so on. So there's like still things like this happening. Plus, there's also quality differences. Now we could basically say, why using X-rays to see if it's brown, green, or white or other color? Because we can basically just see and say, okay, this one's brown, goes to the brown container. Within these groups, there are still quality differences, and it has to be automated process. So what is happening is that there are specific oxides in the glass that are responsible for quality and for color, and those are measured, and they can be measured using XRF. Just as an example, the green color in the green bottle is coming from chromium. So when is it used? Just imagine conveyor belt and a lot of glass coming rushed by. And there are like sorting machines that have XRF modules, and they are doing a fast screening, and then they just sort. And also XRF is used for the more precise analysis of sorted batches that are already like pre-sorted. And then before melting again, the batches are analyzed once more, just to be sure that the correct recycling material is used here. I want to give you two examples for sample preparation for glass samples. First of all, if you're lucky and you have a disc or a plate like this, you can just measure directly without any sample preparation. This is like best case because it's very fast and still a very good measurement. Another possibility when you are having broken glass or powder, there is a fusion as a borate bead. In this case, the glass powder or broken piece is mixed with another glass building material, then fused at a very high temperature to become this kind of disc-shaped glass bead, and then is measured like this. There are some challenges for XRF in every recycling process, but for glass is very easy to measure. This is what can be said about glass, and there is more effort necessary for fusion before measurement of the broken pieces or the powder. This fusion process just takes some time, takes some effort, and basically it's better if we are already having a glass or a disc, but that's not always the case. So yeah. So far about glass. Let's have a look into plastic materials. I would like to introduce to you the example of PET bottles. We now have a new German law which says efficient ways to prevent waste. Preventing waste is always a good idea. So we already have systems with returnable bottles. They are established. You buy a filled bottle, you pay a fee for the bottle. The bottle at some point will be empty because whatever beverage is inside is gone, and then the bottle is returned and the fee is paid back. So this system is already established for years now, and it's working quite well. Now there are like bottles that can be reused and some bottles that are returned that are still like going to waste. And these are the PET bottles. And the PET bottles should now contain more recycling material according to this new law. So minimum 25% from 2025 and 30% from 2030. When we are looking at recycling material that is used for these bottles, the more recycling material we use, the more checks have to be done in all different aspects of the production here. So let's have a look which preparation methods are possible. First of all, if you're having a granule or a powder, then you can prepare a cup and pour the powder in a cup and measure the powder in the cup. This is like the easiest way to prepare a sample for XRF if it's not already a solid sample like the glass. That's the big advantage, that it's so easy. There are some disadvantages, for example, particle size effects or effects because of the air in between the particles. So this also has to be kept in mind when doing this kind of analysis, but it's very fast screening. Another sample preparation that can be done with thermoplastics is the hot pressed pellet. I have this example here, which is obviously not PET bottles, but it's just different colorful plastics that we pour together as granules and hot pressed. But I took this exact picture to show you that pressing a powder or granules as a hot pressed pellet does not change anything about the homogeneity of this sample. So I think this is shown quite well by this hot pressed pellet picture. The homogeneity of the sample is kept even if we are pressing it to this kind of pellet. How is XRF used in this special example? It's used to check impurities, check for impurities in the typical XRF range. As I said before, the typical XRF range is fluorine to uranium. Mostly energy dispersive XRF spectrometers are used for this application. EDXRF spectrometers are these small benchtop devices. They are most of the time also quite cheap or cheaper than the large devices, and those are commonly used for this application. Now we talked about what's possible. Now we can talk about challenges for these plastics measurement with XRF. And first of all, I want to show that there's not all elements that are present in the sample that can also be measured with our device. I showed you the periodic table before. We measure most of the periodic table, but the matrix of these samples, we do not. So hydrogen, carbon, oxygen, and so on, they are not measured when we cannot see it with XRF. So the matrix is hidden from us. We just have to know it and to deal with it. Some devices are still able to distinguish between different plastics, which is actually quite cool that they can do it. So they can at least say it's PET or it's something else. Not all devices can do it, but some can, and some software can do it, and it's this is like the thing that that helps us a little bit with this problem that we cannot really analyze the matrix here. And then the second problem is that we are dealing with inhomogeneous samples. So the sampling will be very important, even more important than it is anyways, because having a representative sample of a batch that is very heterogeneous is very, very hard, and has to be taken very carefully, and it's very important. And if it is necessary, there might be further steps for homogenization necessary. If not for the complete batch, because it's too huge, for the sampling, for the samples themselves. Okay, so that was plastics. Let's have a look onto metal samples. Here we are talking about scrap metals and recycling of scrap metals. These scrap metals are mostly from industry and private waste, and they are collected in these kinds of dumps. And also these scrap metals have to be recycled. In this case, these kinds of handheld XRF devices are commonly used. They have the big advantage that you don't need any sample preparation to use it. You can just hold it to the sample, click a button, measure. Also, the measurement programs, the calibrations, they are mostly predefined by the manufacturer. So you also don't need to calibrate yourself. And the measurement time is only seconds. So you hold it, you press the button, you wait a few seconds, and you get a result. And most of the time, there's even the possibility that it directly displays, for example, what alloy was measured here. So these are very, very commonly used in these kinds of applications with scrap metals. What are the challenges for our XRF measurement? Again, inhomogeneous samples. Again, the sampling is very important in this case. Maybe several points have to be measured. Different points of the batch of the samples have to be measured. And again, we have to be aware that our sample might not be representative for the whole batch. Then we are talking about a short time frame that people are having to look through and sort the scrap metals in this kind of environment. And it has to be easy to use, and it has to be very robust, because I mean, we are talking about this environment, so There has to be a very robust device to work in this kind of environment and get good results. If more precise values are needed than can be taken from this handheld XRF device, there is also the possibility to do fusion as a sample preparation. I already introduced fusion to you when we talked about the glass samples. In this case, it is not as easy because we need a pre-oxidation step. Why is that? Because we are talking about scrap metals, and the metals have the big disadvantage that they form an alloy with the platinum crucibles that we are using for our fusion process because it can withstand high temperatures. The alloy cannot withstand all these high temperatures, so the crucibles will be damaged or even melt inside the fusion machine. That's not what we want. So we need to oxidize our sample beforehand. So what is happening is we are having our sample, we mix it with an oxidizer, an oxidation step is performed, then we get the oxidized sample, and now the same thing as with the glass sample is happening. It's mixed with the glass building material, fusion is happening, it's poured, and then we get the nice fused bead that we saw before. To use the sample preparation, you need a matching calibration. And what is widely used is FLUXANA ferro sets among our customers. FLUXANA sets are application sets that are ready to use. They are coming, for example, as these fused beads, and they can be used directly to calibrate the devices. And these sets can also be extended for a wider range of concentration or elements. And this is widely used. And there are several ferro sets available for different ferro alloys. For example, ferrochromium, manganese, silicon, and we could go on like this forever. So this is what is mostly used for this kind of application. There are also some more metal recycling challenges. I would like to introduce to you metals and oxides might be in one material. Some components can also be present in different oxidation stages, for example, iron. And then this all leads to wrong assumptions, because if I think it's a metal and it's an oxide, I do not know that there's still like oxygen in my sample. If I think it's Fe2O3, but it's a different iron oxide, there might be more or less oxygen inside my sample. And if I'm now going to normalize my sample, I will cause major errors because I don't know my whole sample. So this has to be taken care about. And last but not least, the catalysts. We had a recycling material catalyst for our proficiency test in 2021, and that was a heterogeneous material with oxidic and metal components. So all of the things that I just said are not so good for our analysis were in this material. We got the material delivered here to use it for a proficiency test. And we made some analysis like we always do for our proficiency tests. And we saw that the components, they were not distributed homogeneously enough to do it. So the facility homogenized it once again, the supplier's facility, and sent it back to us. And then we saw that most components are distributed homogeneously enough to do the proficiency test, and that the heterogeneity is still there in a small amount of components. But we said, okay, for most of the components, it's okay. So let's send it to the customers. So we mixed it, we bottled it, we checked again for homogeneity, and we saw it's okay for most of the components. So 2 of 15 components were not okay, but we said we will go with it. The proficiency test was without restriction of preparation or measurement procedures, so it's not an EXA-F only proficiency test. But what we proposed as a preparation was fusion preparation. The same thing as for the metals also goes for the recycling materials, because there's also metal parts. So a oxidized sample had to be used. So pre-oxidation had to happen here. Now I want to show you the results. And just like one of the results that showed very nice the heterogeneity in the sample. In this case, we are talking about aluminium oxide, and we see that the lowest measurement of one of the participants was about 21% of aluminium oxide, and the highest was about 32% aluminium oxide. And here we can see very nicely that that the heterogeneity in the sample makes it very hard to see how the laboratory performed, like in reality. I mean, these results, they include the heterogeneity in the sample plus the uncertainty of each participant of the PT, and it was a very, very interesting proficiency test. The report is available online, so if you're interested in the results or want to chat about these results later, just let me know. So still, even though the results were really bad for some of the components, this recycling material is used as reference with these assigned PT values. Why is that? Because there's simply not so many materials, and there's no materials that like several materials that are available show similar uncertainties. So the assigned uncertainties have to be considered, and especially for the heterogeneously distributed components have to be checked for with each measurement. But it's still like, better than nothing. This is the problem with the reference materials that are mentioned in the very beginning. So let's run through the summary because we are already ahead of time. Recycling material is a very broad term. I think we saw this with all of these examples, and we could go on for hours now and talk about more samples of recycling material. Every material has its own challenge, and within every material, every specific material has its own challenges. But EXA-F can help in many ways when we are trying to analyze these kinds of samples. Still, the results should be questioned and they should be read very carefully. So if you're not sure about your result, you should check for all of the different things that could disturb the results. And what is also very important is that if you're very new to this field, the advice from experts should be taken in consideration when it comes to buying a device type and deciding on preparation technique, because the device type and also the preparation have a major influence on if the measurement and the evaluation of the results is working in the end as intended or not. So thank you for your attention. We rushed a little bit through the end. If there are any questions left, you can also let me know afterwards by just sending an email to me or to our info@FLUXANA email address. I want to tell you not to miss the next applications webinar in November. That will be about glass sets for short-lived samples. All questions will be answered via email in the next days. Yeah, thanks again for your attention, and I wish you a very nice rest of the day.